Let's start with the smallest possible piece of a neural network, one neuron. Forget the biology for a moment. A neuron is just a number machine. It takes some inputs, and it produces a single number. Everything mysterious about deep learning starts right here, with this one humble calculation. Here is the calculation the neuron performs. It multiplies each input by a matching weight, adds all those products together, and then adds one more number called the bias. That sum is the neuron's output before any squashing. It looks like arithmetic, but I want to show you that it's really geometry in disguise. To see the geometry, we collect the inputs into a single arrow, a vector we'll call x, and we collect the weights into their own arrow, a vector called w. Now the neuron isn't juggling separate numbers anymore, it's comparing two arrows living in the same space. Watch what happens to the multiply and add step when we write it with these arrows. Every product pairs a weight with its input, and we sum them all. That exact operation has a name. It's the dot product of w and x. The whole weighted sum collapses into three symbols, w dot x. So what is a dot product really? Geometrically, it measures how much two arrows agree. Take the length of w times the length of x times the cosine of the angle between them. When the arrows point the same way, that cosine is 1 and the product is large. When they're perpendicular, it's 0. Let's feel this with motion. I'll hold the weight vector still and swing the input vector around it. Watch the dot product value on the meter. As the input aligns with the weight, the number climbs to its peak. As it swings to the opposite side, the number plunges below 0. Notice the moment the input is exactly perpendicular to the weight, the dot product is precisely 0, no matter how long the input arrow is. This perpendicular direction is special, and in a minute it's going to become the border between the neuron saying yes and saying no. Here's the key reframing. The dot product w dot x also equals the length of x projected onto the direction of w, scaled by the length of w. In plain terms, the neuron only cares about the shadow that the input casts along the weight's direction. Everything sideways is invisible to it. So a neuron has a favorite direction in space, the direction its weight vector points. Inputs that lean toward that direction earn a big positive score. Inputs that lean away earn a negative one. The neuron is at heart a direction detector. Now let's stop looking at single arrows and start looking at the whole input space at once. Every point on this plane is a possible input. For each point, the neuron computes a number. So the neuron paints a value onto every location in the space. Let's go see that painting. To visualize the value at every point, I'll lift the plane into 3 dimensions. The height above each input point is the neuron's output there. Watch what surface appears when we raise every point to its computed height. It's a flat, tilted plane. Not a bowl, not a hill, not anything curved, perfectly flat, just leaning. That flatness is a direct consequence of the neuron being a simple weighted sum. Straight-line math produces a straight, tilted surface. This is the entire geometric personality of one neuron. Which way does it tilt? Straight along the weight vector. If you stand on this surface and want to climb uphill as fast as possible, you walk in the direction of w. The weight vector isn't just the neuron's favorite direction. It's literally the direction of steepest ascent on this landscape. And the steepness of that climb, it's set by the length of the weight vector. A short weight vector gives a gentle ramp, a long one gives a steep cliff. So the weight encodes 2 things at once in its geometry, which way the surface tilts, and how sharply. Now the fun part. Let's grab the weight vector and rotate it, and watch the landscape respond in real time. As w swings around, the tilt of the whole surface swings with it, like a tabletop pivoting on a central pin. The neuron's opinion of the world rotates as one rigid piece. Pause on any orientation and ask, where is the surface exactly at height 0? That's a straight line cutting across the input space. On one side of the line the output is positive, on the other side it's negative. This 0 line is the neuron's dividing line, and it's perpendicular to the weight. Let's name it properly. This is the decision boundary. Points on the positive side push the neuron toward firing. Points on the negative side hold it back. Almost everything a neuron does for classification lives in the position and angle of this single line. Watch how the boundary tracks the weight. As I rotate W again, the decision line spins to stay perpendicular to it. The weight direction and the boundary are locked at 90 degrees, always. Turn the weight, and the border between yes and no turns with it. But so far, no matter how we rotate, the boundary always passes through the origin. That's a serious limitation. It means the dividing line is nailed to the center of the space. To free it, we finally need the piece we've been ignoring, the bias. The bias is just a constant we add to the weighted sum. Geometrically, adding a constant to every point's value lifts the entire tilted surface straight up, or pushes it straight down, without changing its tilt at all. The slope stays the same, the whole thing just floats to a new height. And here's why that matters. When you lift the surface, the place where it crosses zero moves. The decision boundary slides sideways across the input space, staying parallel to itself. The bias is the knob that lets the boundary leave the origin and sit wherever you need it. Let's separate the two controls cleanly. Rotating the weight turns the boundary. Changing the bias slides the boundary. Direction and offset, angle and position. Between those two moves, you can place a straight dividing line absolutely anywhere in the space at any angle. Let me make this concrete with a task. Suppose we have blue dots and orange dots scattered on the plane, and we want the neuron to tell them apart. Success means finding a straight line with all the blues on one side and all the oranges on the other. Watch me solve it by hand, using only the two knobs. First, I rotate the weight until the boundary's angle matches the gap between the clusters. Then I slide the bias until the line sits cleanly in the empty lane between them. That's it. The neuron now classifies these points. This is the whole story of a single neuron, and also its ceiling. It can only ever draw one straight line. Give it data where the two colors are tangled in a way no straight line can separate, and one neuron is simply stuck. Let me show you such a case. Try as I might, rotating and sliding, there's no orientation of the line that gets all blues on one side. A single neuron carves the world into exactly two half-planes, and that's all. To do better, we can't make the neurons smarter. We have to add more neurons. So let's introduce a second neuron, sitting right beside the first. It looks at the very same inputs, but it has its own weight vector and its own bias. That means it has its own favorite direction and its own decision boundary, completely independent of the first. Give this second neuron a different weight direction, and its boundary cuts the plane at a different angle. Now we have two lines crossing the input space. Already the picture is richer. Two lines can do things one line never could. Look at where the two lines cross. They chop the plane into four regions, like slicing a pizza with two straight cuts. Each region is defined by a distinct combination, positive or negative for the first neuron, positive or negative for the second. Let's read those regions as signals. In each area, ask each neuron, are you positive or negative here? Neuron 1 says plus, neuron 2 says minus, that's one region's signature. Flip either answer and you're in a different region. Two neurons give every location a two-part label. This is the crucial shift. A single neuron gave a location one bit of information, which side. Two neurons give it a richer code. The pair of outputs together pin down which of several regions you're standing in. The neurons have started to work as a team, building an address for every point. Now let's add a third neuron, with yet another weight direction and bias, and its own boundary slicing across at a new angle. 3 lines on the plane. Watch how many regions we can carve out now. 3 lines placed generally can divide the plane into as many as 7 regions. Each region is a small territory with its own unique combination of 3 signs, positive or negative from each of the 3 neurons. The flat plane has become a patchwork of labeled tiles. These 3 neurons, all reading the same input and each producing one number, are what we call a layer. A layer is just a handful of neurons working in parallel on the same input. And geometrically, we've just seen exactly what a layer does. It carves the input space into regions. Let's stack the 3 tilted surfaces to feel it in 3 dimensions. Each neuron contributes its own flat, tilted plane over the input space. 3 planes leaning 3 different ways. Their combination is what encodes those regions down below. Here's a way to summarize the layer's whole effect. Take any input point and record the 3 outputs as a list of 3 numbers. That list is a new location. The layer has taken a point in the original space and moved it to a point in a new three-dimensional space. It's a translator between spaces, and that new space is where the magic hides. Points that were hopelessly tangled in the original plane can land far apart in the new space, simply because the three neurons scored them differently. The layer's job is to rearrange the data into a shape that's easier to separate. Remember the tangled dataset that defeated a single neuron? Watch it now, transformed by our three-neuron layer. The points that no straight line could split in the original plane have been rearranged. In the new space, a straight cut suddenly works. That's the quiet trick at the heart of neural networks. A layer doesn't classify by brute force. It reshapes the space so that a hard problem becomes an easy one. Each neuron is still just a weighted sum drawing a straight boundary. The power comes from combining several of them. Let's zoom back out and connect the geometry to the arithmetic one last time. Each neuron's weight vector set the tilt in the direction of steepest climb. Each bias slid its boundary off the origin. Together, the layer's weights and biases decided how the whole space gets folded and stretched. And where do all those weights and biases come from? Learning. When a network trains, it is nudging every weight vector to point a little better and every bias to sit a little truer. In geometric terms, training is the slow rotating and sliding of all these boundaries until the regions line up with the data. Picture the earlier landscape tilting and shifting on its own now, searching. Each small adjustment lowers the number of mistakes. The weight vectors swivel toward the directions that matter. The biases drift to center the boundaries. That searching motion is exactly what gradient descent does. Now imagine feeding the output of this layer into another layer, and another after that. Each layer carves and reshapes the space the previous one handed it. Regions of regions, folds upon folds. That stacking is where the astonishing flexibility of deep networks comes from. But never lose sight of the atom we started with. Every one of those folds, in every layer of the deepest network, is built from this one move. An input vector, a weight vector, a dot product, a bias, a tilted plane, and a line that says yes on one side and no on the other. So the next time you hear that a neural network is a black box, remember what we drew today. At the bottom, it's not mysterious at all. It's arrows agreeing or disagreeing, planes tilting toward their favorite directions, and straight lines sliding into place to carve the world into regions. One neuron draws a line, a layer carves regions. Stack them, let them learn, and straight lines start to bend the world into shapes we could never have drawn by hand. That's where we'll pick up next time. Thanks for thinking through the geometry with me. If this made it click, subscribe for more visual math.